magnet from the prior page are circular, meaning the magnetic field in a bar magnet passes through the center of the bar magnet and comes out of the bar magnet. It goes back through. It forms a circular path through the object, which is why when you break a bar magnet up into pieces, you can't break off a north end and a south end of a bar magnet. If you break the bar magnet into pieces, you get a new north side and a new south side. You don't break away the north end of the magnet and the south end of the magnet. And I don't care whether you understand it or not, doesn't matter. This is what happens. There are no magnetic monopoles. There is no north pole that is a single point in a magnet. Again, where the magnetic field comes from inside a bar magnet is not obvious. And that's not the point of today's discussion. The point of today's discussion is to understand that the magnetic field is dynamic, it is circular, has no point of origin and no point of termination, and exists only because there is a movement of a charged particle. The moment I stop the movement of this particle, the magnetic field would disappear, it would go to zero. Now, charged particles didn't experience a magnetic force unless they were moving. That was the big takeaway from last week, that a single point charge in space could not be started into motion nor stopped by the action of a magnetic field. That a charged particle had to already be moving, and it moving through space in a region with the magnetic field caused a force on the charged particle. So it shouldn't surprise you that a particle that sits still in space, although generates an electric field, does not generate a magnetic field. So remember, the electric field is going to still be there. I'm not going to be drawing in the electric field. I'm going to focus on the magnetic field today, okay? Now, the moment we give that particle a velocity, however we choose to do so, the moment that particle has a velocity, it begins to immediately produce a magnetic field. Now, that magnetic field is a little bit interesting in that the magnetic field produced by a moving charged particle is circular. It's circular. And to understand the direction of this circle, it's a right-hand rule procedure. It's the curl rule. And if you were to point your thumb in the direction of the velocity, your fingers will curl in the direction of the magnetic field created by the moving charged particle. So, thumb this way, I have a circular field, and to try and put a clearer understanding about that, that circular field is out of the board on top of the particle and into the board below the particle. So it's a circle though. So if I were to draw this particle with a velocity coming straight at us, so this is the same charge, but coming straight at us, the magnetic field would be circular in that direction as it approaches us. Again, right-hand rule, velocity out of the board, magnetic field is wrapping around it in a counterclockwise direction from the board towards you. There's a lot to unpack here that's not obvious, and I want to draw your attention to it. First, in the first picture, you'll notice how I made the circles smaller and they got bigger and then smaller again. This magnetic field is got a distance component related to it. So if I was located, say, here at point P, as this particle passes me, I would detect a magnetic field that was increasing in strength and then decreasing in strength as it passed me. So the size of this magnetic field is proportional to how far away from the particle you are. But this isn't static. So it's hard to recognize the fact that it's producing a magnetic field that is tapering off the further away you are from the particle, but the particle is moving. So you're going to get this effect of the magnetic field increasing and decreasing as the particle passes by you. Now, we'll get to the mathematics of that in a bit. I think this is already quite a bit to unpack, but there's also something more important than I said. This is the most important thing I'm going to say when it comes to the structure of the magnetic field. Magnetic fields have no point of origin and no point of termination. Electric fields, say, originated at positive charges and terminated at negative charges. They had a clear point of origin and a clear point of termination. Magnetic fields do not. There's no origin or termination of a magnetic field. It is a perfect loop. All magnetic fields, even the ones, the law that's designed to help us understand the size of the magnetic force is no fun at all. It's Biot Savarte, and I have no idea of the history of the Biot Savarte law, why there's two names. I'm sure it's not the same person with a hyphen. I'm pretty sure it's two different people are credited with this work. And the work predates point charges. So I want you to understand that all of the work that went into the Biot Savarte law that we're going to see now was based on the flow of current, which we also know is the flow of positively charged particles in a wire. So what we have is a conglomeration of lots of testing that has kind of given us this law. We won't be using this law very much, and you'll be happy to know that we won't be using this law very much. But this law is supposed to be able to tell us the size of a magnetic field at some point in space where there might be moving charged particles. So this law is from the standpoint of point P. And it would tell us the magnetic field at point P. Please understand that this magnetic field assumes that the particle is at a certain location, but we know that particle is moving. So the Biot Savarte law can't tell us very much because the particle keeps changing position. You understand? Whatever we get through the Biot Savarte law, it's transient. So obviously, I think there's some things we're going to need here in using the Biot Savarte law. And the first one is we probably need a variable that relates how far away we are from where the particle is. And we traditionally use lowercase r for this. Again, please stop using the word radius here. This is just a distance from the moving charged particle to our location in space. The magnetic field produced by a single point charge is proportional, and it's proportional. I'm going to have to kind of move this over here because I need room. The Biot Savarte law is big. The Biot Savarte law is going to be proportional to several factors, and I think you kind of know what these factors probably are. Like, it probably has a distance component to it, like how far away we are from the particle. It probably has something to do with the size of the charge, and it probably has something to do with the speed at which the particle is moving. So I think it makes sense that all of those things would probably play a role in determining the size of the magnetic field. But of course, like anything else, there's a proportionality constant too. So I'll put the proportionality constant out front. And I'll fill that in just a minute. But the way that these things interact is a little bit bizarre. There's going to be the charge, Q. And then there's the velocity. And then there is separation distance. So the magnetic field has a similar proportionality restriction as we have for Coulomb's law and the electric field, that it is proportional to our distance away squared. Unfortunately, just like electric fields, magnetic fields are vectors. And the direction of the magnetic field is related to the direction of the velocity, but also related to where you are relative to the particle, making our next part a little less fun to write. You see, the direction of the magnetic field is related to the direction of the particle from you. But r is in the denominator of this relationship. Therefore, we put v cross r hat up here to say that the direction of the magnetic field is the cross product of the velocity and a single unit vector directed along r. This portion is to give direction to the magnetic field and only give direction to the magnetic field. R is a unit vector, so it doesn't change the size of this value. It just helps us with the right-hand rule and to give us how much of our angle is perpendicular to the velocity. So I know it's a lot to take in, but this is Biot Savarte law. There is a constant of proportionality. The constant of proportionality has a new constant called the permeability constant, and it has 4 pi embedded in it. Mu naught over 4 pi is the thing that's all over this particular calculation. In the same way that K was related to 1 over 4 pi epsilon naught, we find that in magnetic fields, it's mu naught over 4 pi. So these are similar constructs. The permittivity and the permeability constant pollen counts high today. These words are just kind of created. Permittivity, permeability, they're not anything that has to really, like there's no real difference in what these constants say. They mean the same thing. They're both trying to impress upon you the idea that this is how well an electric field or magnetic field can be established in a vacuum. So we say the permeability constant is how well a magnetic field can be established in a vacuum, and we say the permittivity constant is how well an electric field can be established in a vacuum. They have kind of some weird properties. Weirder still are the units of these properties. The big important difference here is that we have found that these two things are related, and they're related in a really weird way. And we're going to come back to that in a little while, probably a couple of weeks, but they're related by the speed of light, meaning they are both proportional to the speed of light and therefore proportional to each other. These two measurements are apparently directly related. The electric field and the magnetic field are not very different from each other. They appear to behave very different, but they're not. They must have lots of things that are related in common. Also, mu naught is known exactly, where the permittivity constant isn't. The permeability constant is an exact number. And we'll talk a little bit about what it's about in a little bit. But again, the permeability of free space. So remember how often we saw the permittivity constant all of first semester? So mu naught is the constant for magnetic fields. And we're going to see it a lot. All of our answers all are going to end up with a mu naught in them somewhere. And because you see it in the numerator of this fraction, you better believe whenever you're asked to calculate the magnetic field, you should expect a mu naught in the numerator. The 4 pi, on the other hand, just like the 4 pi with the in the permittivity constant, it tends to get canceled out by things. The circular nature of the magnetic field is probably evident in why 4 pi shows up here. But let me not digress too far and say that consider, please, the right-hand rule that's being suggested here. It needs to be in agreement with the curl rule. We know that here, we expect the magnetic field to become out of the board because that's what the curl rule would supply, but the 3-finger rule should tell us that too. Remember, it is V cross R. So for V and R to be in the same direction, I have to have my thumb out of the board, which is why V cross R and why R is drawn in this way, from the particle to our location in space. But we apply it here, saying the magnetic field is out of the board at this location. I want you to see that, but in practice, it will always be easier to use the curl rule to determine direction of magnetic fields. And so I just use the curl rule. Point your thumb in the direction of the velocity, and your fingers curl in the direction of the magnetic field. But before you leave, cross product is going to always produce a sine of an angle all the time. So all calculations for the magnetic field from a point charge involve the sine of this angle, the angle between R hat and V, telling you that the magnetic field is max when the R is perpendicular to V. So when it's like right down there, that's where you're going to get the maximum magnetic field. All right.